Up to this point in these lectures, I've only discussed black holes and gravitational collapse using the idealization of spherical symmetry. In this lecture, I want to talk about black holes in more general terms. Let's begin by describing the geometry of a rotating black hole in vacuum. This is the Kerr black hole, or the Kerr solution. We can write the metric in coordinates that are referred to as Boyer-Lindquist coordinates. And the coordinates are t, r, theta, and phi. And in these coordinates, the metric is minus 1 minus 2mr over rho squared, and I'll define rho in a minute, times dt squared, minus 4ma, I'll define a in a moment, times r sine squared theta, divided by rho squared, d phi dt, plus rho squared over delta, I'll define delta in a moment, times dr squared, plus rho squared d theta squared, plus r squared plus a squared, plus 1 over rho squared times 2m r a squared sine squared theta, all of that times sine squared theta d phi squared. Now rho squared, which appears in several places in this metric, in this line element, is defined as r squared plus a squared cosine squared theta. And delta, which appears here, is defined as r squared minus 2mr plus a squared. Now the other parameters you see are m, which is the mass of the black hole, and this parameter a, which is defined as j over m, where j is the angular momentum of the black hole. One thing we can check right away is the special case in which the angular momentum vanishes. All right, this should be a non-rotating black hole in that case. You'll notice that if j is 0, then this parameter a is 0, the angular momentum per unit mass is 0, and that means rho squared is just equal to r squared, and delta is equal to r squared minus 2m times r. So this coefficient of dt squared is just minus 1 minus 2m divided by r. That's the same coefficient of dt squared that we have for the Schwarzschild metric and Schwarzschild coordinates. This coefficient goes to 0 because a is 0. This coefficient is r squared divided by r squared minus 2mr, so that's 1 divided by 1 minus 2m over r, the same as the GRR component of the Schwarzschild black hole and Schwarzschild coordinates. This is r squared d theta squared, and finally here we have these two terms vanish, so this is r squared sine squared d phi squared. So you can see that when j is equal to 0, the Kerr black hole is just a Schwarzschild black hole. In particular, the Kerr metric in Boyer-Lindquist coordinates just becomes the Schwarzschild metric in Schwarzschild coordinates. So how do we know that these parameters m and j represent the mass and angular momentum of the black hole? So how do we identify m and J as mass and angular momentum. Well, we can identify M as the mass the same way we did for the Schwarzschild black hole by releasing a satellite near infinity in the asymptotically flat region and measuring its orbital period, then applying Kepler's third law. But identifying the angular momentum is a bit more difficult. What we can do is examine the metric far outside a weakly gravitating body and show that it has the same form as the Kerr metric in the r goes to infinity limit. So we examine the metric outside a weakly gravitating mass or weakly gravitating body, and we show that it has the same form as the Kerr geometry in the asymptotic region as r goes to infinity. When we do this, when we relate the Kerr geometry in the asymptotic region to the metric outside a weakly gravitating body, we find that the Kerr parameter m is given by the integral of t00 integrated over all space. So this is the 0,0 component of the stress energy momentum tensor for the weakly gravitating body, and it's in a nearly Newtonian frame, so we're in the rest frame of the body. So this is the energy density of the body. So the integral of the energy density is the total energy or total mass of the body. And in a similar way, we can identify the Kerr parameter J as the integral of x times t0y minus y times t0x. And here x and y refer to the Cartesian coordinates in the nearly Newtonian frame of this weakly gravitating body integrated over all space. So this is, in this frame, t0y is just the momentum density in the y direction. This is the momentum density in the x direction. So this is just the total angular momentum of the body. And that's how we can identify m and j as the mass and angular momentum by their effects on the geometry in the asymptotic region. Now let me point out some of the key features of the Kerr geometry. You'll notice that in Boyer-Lindquist coordinates, the metric components are independent of the coordinate t, and they're independent of the coordinate phi. So that means we have two killing vector fields, d by dt and d by d phi. So one of the killing vector fields is d by dt, and this vector field is time-like outside the black hole, so this corresponds to a time translation symmetry and shows us that the black hole is stationary, but in fact it's not static as the Schwarzschild black hole is, because this vector field is not hypersurface orthogonal. The other killing vector field we identified was d by d phi, so this tells us that the Kerr black hole has an axisymmetry. In other words, a symmetry under rotation is about what we sometimes refer to as the z-axis. But it's not spherically symmetric like the Schwarzschild black hole. So these two killing vector fields, which we easily identified from the Kerr metric written in Boyer-Lindquist coordinates, these are in fact the only two killing vector fields of the Kerr geometry. One of the physical consequences of a black hole's rotation is that it drags the inertial frames in the direction of rotation. So recall that an inertial frame is a reference frame of a freely falling observer. So let's consider an observer who falls freely from r equal infinity with no angular motion initially towards the rotating black hole. We can solve for the motion of this observer by solving the geodesic equations. So let x mu dot be the forward velocity of the observer. That's t dot, r dot, theta dot, phi dot, where dot denotes differentiation with respect to proper time. So this is the forward velocity. And let's restrict the motion to the theta equal pi over 2 plane. So then, in particular, theta dot will be 0. And now, because we have two killing vector fields, namely d by dt and d by d phi, we have two constants of the motion. Namely, what we'll call little e, which is the inner product of d by dt and x dot and the forward velocity, and little l, which is the inner product of d by d phi and the forward velocity. So these are first integrals of the geodesic equations, and we can evaluate these constants anywhere along the geodesic since they're constant. So in particular, if we look initially at the initial time, the observer is at rest at r equal infinity. So r dot and phi dot are 0, and t dot is just 1, because at infinity the Kerr geometry is asymptotically flat and the Boyer-Lindquist coordinates just reduced to Minkowski coordinates. So in particular, the Boyer-Lindquist time coordinate t coincides with proper time for an observer who's at rest. So t dot is 1 initially. So let's use this initial data to evaluate E and L. First, for E, we have the inner product of d by dt. That's the vector with components 1, 0, 0, 0. And the inner product uses the metric, which at r equal infinity is just the Minkowski metric, minus 1, 1, 1, 1 down the diagonals. And then x dot initially is just 1, 0, 0, 0. So this is minus 1. E is minus 1. And now for L, we have the vector d by d phi, which has components 0, 0, 0, 1, times the metric at infinity, times the initial forward velocity, and that's just equal to 0. So little l is 0. So the geodesic equations for our observer who's falling towards the black hole have the first integrals of these equations given by the inner product of d by dt with the forward velocity is equal to minus 1. The inner product of d by d phi with the forward velocity is 0. And of course there's one other first integral of the equations of motion, that is the normalization condition that the forward velocity should be normalized to minus 1. Now these three equations can be used to solve for t dot, r dot, and phi dot. Remember, theta dot is 0. The results are t dot equals r cubed plus a squared r plus 2a squared m divided by r times r squared minus 2mr plus a squared. R dot is equal to minus the square root of 2m over r times the square root of 1 plus a squared over r squared. and phi dot, remember theta dot is 0, this is equal to 2am divided by r times r squared minus 2mr plus a squared. Now these equations are pretty straightforward to solve numerically, but let's see what we can learn by just examining the form of these equations. And remember, these equations describe an observer who's falling freely into the black hole, starting near r equal infinity. And near r equal infinity, r dot is close to 0, but it's negative. So the r value of the observer decreases, and it continues to decrease without any limit until, in these coordinates, what happens is the integration breaks down when this factor, r squared minus 2m over r plus a squared, which appears in the denominator here as well as here, when that factor goes to 0. And that value of r that makes this 0 is the black hole horizon. So what happens is the observer hits the horizon, the observer passes through the horizon, but in these coordinates, the integration breaks down. So these are not good coordinates to describe the geodesic infall all the way through the horizon. But up until the observer hits the horizon, these equations are perfectly fine. Now the other thing you'll notice about these equations is the phi dot equation. When r is near infinity, phi dot is close to 0, but as r decreases, phi dot begins to increase. So the observer develops some angular motion in the direction given by the sign of A. That's the sign of the angular momentum. So this is the effect that we refer to as the dragging of inertial frames. So let me draw a picture of the black hole. This is a top view looking down the z-axis. So this is the horizon of the black hole. It's rotating in this direction. Now this is a phi equal constant coordinate line. And our observer, who begins out near infinity, falls in towards the black hole, but is swept along by the rotation of the black hole. So the observer hits the horizon, but the trajectory is swept away from this radial line by the rotation of the black hole, and that's referred to as the dragging of the inertial frames, the inertial frame defined by this freely falling observer. Let's take another look at the Kerr metric and Boyer-Lindquist coordinates. You'll notice that some of these metric components vanish or go to infinity when rho squared is 0 or when delta is 0. So we need to examine the properties of the geometry when rho squared is 0 and delta is 0. In particular, we want to know if these correspond to true curvature singularities or simply coordinate singularities. And one way to do that is to examine curvature and variance. So for example, we can look at the square of the Riemann tensor. So r mu nu sigma rho, r mu nu sigma rho. And if we compute this for the Kerr geometry, what we find is an expression that looks like a complicated function of r and theta in the numerator divided by rho to the 6th power. So this shows that when rho goes to 0, there's a true curvature singularity. On the other hand, when delta equals 0, there's no problem with the curvature, and we can examine other curvature and variance and find the same result, namely that delta equals 0 is merely a coordinate singularity. Whereas rho squared equals 0 is a true curvature singularity. So let's examine this curvature singularity. So the curvature singularity occurs when rho squared is equal to 0, and if we recall, rho is defined as r squared plus a squared cosine squared theta. So rho squared equals 0 requires both r equals 0 and theta equals pi over 2. Now, to understand the nature of this singularity, we need to examine the r equals 0 subspace within a t equal constant surface. So let's examine r equals 0 in a t equal constant surface of the space-time. So setting r equals 0 and t equal constant, we have dr and dt are both 0, and also from their definitions, rho squared is a squared times cosine squared theta, and delta is equal to just a squared. And then the line element, or the metric, becomes a squared times cosine squared theta d theta squared plus a squared sine squared theta d phi squared. So this is the geometry of r equals 0 within a t equal constant surface. And we can write this in a little bit more familiar looking form by changing variables. Let's define a radial coordinate. Now I don't want to use the letter r. Let's say r tilde. Let's let r tilde equal sine theta. Then dr tilde is equal to cosine theta d theta. And this metric becomes ds squared equals a squared times dr tilde squared plus, I'll factor out the a squared, plus r tilde squared times d phi squared. So this is just the metric for a flat two-dimensional plane in polar coordinates. And you'll notice that as theta ranges from 0 to pi, r tilde ranges from 0 up to 1 and then back down to 0 again. So the maximum value of r tilde is 1. So that means this is a disk of radius a. And in fact, these coordinates cover the disk twice, once as theta ranges from 0 up to pi over 2, and then again as theta ranges from pi over 2 to pi. But the rim of the disk, or the edge of the disk, at theta equal pi over 2 is a circle or a ring of radius a. And this is the singularity. The singularity is that theta equal pi over 2, the edge of this r equals 0 disk. So this is referred to as the ring singularity. The singularity of a Kerr rotating black hole is called the ring singularity. Now we noted before that the Kerr geometry has a coordinate singularity at delta equals 0. And just like in Schwarzschild, the coordinate singularity, it's not a curvature singularity, but it still has significance. It's the horizon of the black hole. So delta was defined as r squared minus 2mr plus a squared. So if we solve this equation, we find there are two roots. They are m plus or minus the square root of m squared minus a squared. So there are actually two black hole horizons. An inner horizon and an outer horizon. And I've labeled those two horizons as R plus and R minus. Now you'll notice in the limit as A goes to 0, as the angular momentum of the black hole vanishes, the R plus horizon is 2m. That's the Schwarzschild horizon. The R minus horizon is just 0, so it doesn't exist for the Schwarzschild black hole. Or said another way, that second inner horizon just coincides with the singularity for Schwarzschild. Now, from the perspective of an outside observer, it's the outer horizon that matters. So that's what we'll refer to as the event horizon. Is this R plus horizon, which is given by m plus the square root of m squared minus a squared. Now this horizon plays the same role as the Schwarzschild horizon. If any particle or observer crosses this horizon to smaller values of little r, then they can never return, and an outside observer can never receive any signals or information from the interior inside this event horizon. Now, one thing you'll notice about this expression for the event horizon is that it requires m squared to be greater than a squared. So it exists only if a squared is less than m squared. So if a squared is greater than m squared, then we have no horizon, but we still have a singularity. So in this case, the singularity is not hidden behind an event horizon, and it could in principle be seen by observers out near infinity. This is referred to as a naked singularity. I'll have more to say about naked singularities in a few minutes. For now, let me give you a quick summary. The Kerr geometry describes a stationary rotating black hole in vacuum, and it's parameterized by two parameters, the mass, m, and the angular momentum, j. Now, if instead of vacuum, if we had electromagnetic fields, then we could write down what's known as the Kerr-Newman geometry, which describes a stationary rotating black hole that's also electrically charged. So this black hole is parameterized by mass, m, angular momentum, j, and electric charge, q. So this is a three-parameter family of black hole solutions. That is, solutions of the Einstein equations with the stress-energy momentum tensor given by the electromagnetic field. Now, the Kerr-Newman geometry that describes a charged black hole is pretty interesting theoretically, but from a physical or astrophysical standpoint, it's probably not very relevant. After all, matter is pretty much neutral on average, electrically neutral, so we would expect any black hole that formed by gravitational collapse to have charge equal to 0 or very close to 0. So what do we know about black holes in general, apart from the particular example of Kerr and the special case of Schwarzschild? Well, one thing that we can do is write down solutions that correspond to small perturbations of Kerr. So we can construct solutions that are small perturbations of the Kerr solution. And what always happens if we run this forward in time is that the perturbations radiate away as gravitational waves. The waves either radiate to infinity or radiate down across the horizon into the black hole interior. So the perturbed Kerr solution always settles down to a simple unperturbed Kerr black hole. But are there other types of black holes that aren't just simply perturbations of Kerr? Well, what we know and what's been proven is that a horizon always contains a singularity. Now, by singularity here, I don't necessarily mean a curvature singularity. What is meant by singularity is that time-like geodesics can't be extended for an infinite proper time once they cross the horizon. So time-like geodesics end in finite proper time. So, of course, our generic examples of the Kerr black hole, Kerr-Newman, and Schwarzschild all have the time-like geodesics ending at a curvature singularity. Moreover, we don't know of any cases of a horizon that contains a non-curvature singularity, so it appears likely that all horizons contain a curvature singularity. Now we can turn this around and ask the question, is a curvature singularity always hidden behind a horizon? A curvature singularity that's not hidden behind a horizon but can be seen by observers out to infinity is referred to as a naked singularity. Now we already found from our study of the Kerr solution that if the angular momentum per unit mass squared is greater than the mass squared, the solution corresponds to a naked singularity. So we have at least this one example of a solution of the Einstein equations that corresponds to a naked singularity, but the question remains as to whether or not such a solution is relevant physically, if naked singularity actually occurs in nature. So we have evidence from both theoretical and numerical studies that a naked singularity won't form from natural physical processes. So for example, you can start with a Kerr black hole with a squared less than m squared and try to spin it up by throwing in matter with a lot of angular momentum. And invariably what happens is it doesn't work. You can increase the angular momentum, but you also increase the mass in such a way that a squared always remains less than m squared. So it appears that you can't spin up a Kerr black hole that would be a black hole with a squared less than m squared to produce a naked singularity. Now in 1969, Roger Penrose formulated what's known as the cosmic censorship conjecture, which says that naked singularities can't exist in nature. With the possible exceptions of the Big Bang and the Big Crunch. So this conjecture would require any singularity to be hidden behind a horizon. Now, these questions of naked singularities and cosmic censorship continue to be an area of active research. At this point, I think it's fairly clear that the cosmic censorship conjecture is false in the sense that Einstein equations do allow for the possibility of naked singularities, but that still leaves open the question of whether naked singularities play a significant role astrophysically. In other words, we still don't know if there are any naked singularities floating around in the universe, and we don't know if naked singularities can be formed by any natural physical processes. So now let me turn to the related question of gravitational collapse and ask the question, what do we know about gravitational collapse in general? So in particular, without making the assumption of spherical symmetry. Well, we don't have a bunch of theorems to address this question, but we do have expectations that are supported by theoretical calculations and numerical simulations. So the expectation is that an isolated star, when it collapses, it will quickly settle down to form a Kerr black hole. This is referred to as the no-hair conjecture. Or the no-hair theorem. And it's really quite remarkable. Remember, a Kerr black hole is characterized by just two parameters, the mass and the angular momentum. So this theorem is telling us that no matter how complicated the star might be initially, after it collapses, it's characterized by just two parameters, m and j. So here's our star initially, and it contains lots of detailed structure, different types of matter in different layers, and various processes are occurring. Nuclear fusion is causing distortions and waves and flares on this star. But when it collapses, all of this detailed structure, all of this hair, disappears. It's either radiated out to infinity or swallowed up into the black hole. So the only properties of the star that remain are its mass and its angular momentum.